started. We're going to be learning more Erlang today. We're on the concurrency chapter. If you haven't been watching, I have a YouTube series with the playlist with the previous videos on Erlang. And yeah, Erlang is a language built in 1986 um, by Ericsson. It's like a phone company. Um, Joe Armstrong was one of its creators. And oops, I have messages coming in. That's probably yeah. But yeah, it's really good for concurrency, and that's what we're going to be hitting today. So that'll be kind of cool. Should be fun. But I think there's a lot of talking in the very beginning. We're reading this book called Learn You Some Erlang for Great Good. Um, my brain is just not moving today. It's like, say something, brain. And it's just like, yeah, there's a book. That's it. We've been using it. We've been going through it. It's um it's in my YouTube description in previous videos, so if you want to find it or follow along, you can do that. It's been pretty good so far. Um yeah, I'm annoying myself. So, before we start, what's been going on? My life today is going well, sort of. I woke up at 1 p.m. and I just couldn't get up. I woke up at like 8 the first time or maybe even 7, and I was just like, nah, this isn't working. I wake up again the next hour. I think I go to the bathroom, which was my mistake, like because I went to the bathroom and then I went back into bed, and that's like death because going to the bathroom is the only reason I stay out of bed. So I just kept waking up every hour and having crazy dreams. I don't know how many of you have this, but like I basically like fly in my dreams like every night. Um yeah, it's kind of weird. And I fly the same way. It's never like Superman flying. It's just like kind of just launch up into the air. Um it's kind of weird. Anyway, I went running. It's like 3 times. It's the third time I've gone running in the last 7 days. Before this, I didn't do any exercise. So, like, I've run before, like years ago, but it's been a while. So, I'm starting out carefully. I'm trying not to go all at once. So, I just go first day, I just went around the block. Then, second day, I went, I don't know, probably it's like a quarter mile. And today I probably went like somewhere between half and 3/4 mile. So that double that for kilometers. Um, so yeah. But today it was so windy, like the windows don't close super well. So when um when the wind was like blowing so hard it was getting through the window, and it was just like whistling woo the whole time, and that kept waking me up also. Yeah, I don't get it. It was pretty annoying. All right. I am not super oops, sorry. I'm not super motivated today. So we'll see how this goes. I really hope that I can get more into it. Just feel tired, blah. Even though I like ran today, I went to the supermarket, I did laundry. It's like I was a good adult human being today. I even took care of some bills, but yeah, it just didn't go that. I just feel kind of blah. And I'm trying my mouse on my left hand today. I like switching it up every so often. My partner is away. I miss her so much. That's probably why I feel blah, right? Because she's not here. I usually don't stream so late, so I don't know. Okay, let's go look at Erlang. We're going to do this. We're going to kick ass. Learn you some Erlang for great good. The Hitchhiker's Guide to Concurrency. That's a reference to Hitchhiker's Guide to the Galaxy by Douglas Adams? I think it's Adams. Yeah, Adams. He died in 2001. Good book, though. Far out in the uncharted backwaters of the unfashionable beginning of the 21st century lies a small subset of human knowledge. It kind of has Hitchhiker's Guide vibes. Within this subset of human knowledge is an utterly insignificant little disciple whose von Neumann descended architecture is so amazingly primitive that it's still thought that RPN calculators are a pretty neat idea. This is totally Hitchhiker's Guide sort of writing in the very beginning of the first book. This discipline has, or rather had, a problem, which was this. Most of the people studying it were unhappy for pretty much of the time when trying to write parallel software. Many solutions were suggested for this problem, but most of these were largely concerned with the handling of little pieces of logic called locks and mutexes and whatnot. Which is odd because, on the whole, it wasn't the small piece of logic that needed parallelism. And so the problem remained lots of people were mean, and most of them were miserable, even those with RPN calculators. We did RPN, reverse Polish notation, in a previous video. Many were increasingly of the opinion that they'd all made a big mistake in trying to add parallelism to their programming languages, and that no program should have ever left its initial thread. It says, parodying The Hitchhiker's Guide to the Galaxy is fun. Read the book if you haven't already. It's good. I agree. This is totally why I started using Elixir. I hated sort of always being stuck with locks and mutexes and always having, like, if you get a deadlock, debugging it so hard. So it was just very, very annoying. Don't panic. That was the big slogan for Hitchhiker's Guide. Hi, today or whatever day you are reading this, even tomorrow, I'm going to tell you about concurrent Erlang. Chances are you've already read or dealt with concurrency before. You might also be curious about what the emergence of multi-core of the emergence of multi-core programming. Anyway, the probabilities are high that you're reading this book because all of this talk about concurrency going on these days. A warning though, this chapter is mostly theoric. Is that a word? I thought it was like theoretical. If you have a headache, a distaste for programming language history, or just want to program, you might be better off skipping to the end of the chapter or skip to the next one, where more practical knowledge is shown. Hey, Findus. Good to see you. It's kind of late, right? I've already explained in the book's intro that Erlang's concurrency was based on message passing and the actor model, with the example of people communicating with nothing but letters. I'll explain it more in detail again later, but first of all, I believe it's important to define the difference between concurrency and parallelism. All right, guys, what do you think the difference between parallelism and concurrency is? Boo, 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 boo. So it's not like I really remember. Well, I guess if you think of the word, it kind of makes sense. Concurrency, well, I don't know. Concurrency, one of them, and I think it's concurrency, just means that two things are running at the same time in the sense that they started at the same time, but doesn't mean that they're actually being executed at the same time. So when you have like a JavaScript thing where you have cooperative threads, like one is running, then it says, okay, the other guy can run. And you basically take turns getting executed. So it gives you the illusion that two things are going on, but they're not really. Parallelism is when they are independently running. So on computers, it means on different cores or whatever. Now, the book's going to say that a shit ton better than I just did. So let's see what it says. In many places, both words refer to the same concept. I know it's so late in the evening, right? But like I was bitching about this earlier, Findus. Like I just felt blah all day today. I woke up at like 1 or 2 p.m., sort of out of bed. I even went running, but it's like gray out. It was kind of wet. I went I did stuff. I went grocery shopping. I did laundry, but I just don't feel good. But and my partner's out. So I'm just starting now. We'll see how it goes. They are often used as two different ideas in the context of Erlang. For many Erlangers, concurrency refers to the idea of having many actors running independently, but not necessarily all at the same time. Parallelism is having actors running exactly at the same time. I will say that there doesn't seem to be any consensus on such definitions around various areas of computer science, but I will use them in this manner in this text. Don't be surprised if other sources or people use the same terms to mean different things. So, parallelism is like concurrency plus plus because it's really running independently in different cores or different machines even, right? Like they don't even have to be on the same machine. Yeah, I think it was like all over Europe, right? Not good. This and so windy. It was so windy today and it's still windy. This is to say Erlang had concurrency from the beginning even when everything was done on a single core processor in the 80s. Each Erlang process would have its own slice of time to run, much like desktop applications did before multi-core systems. Parallelism was still possible back then. All you needed to do was have a second computer running the code and communicating with the first one. So their first version of parallelism is like two independent machines that somehow the program would communicate over the network with, it sounds like. Even then, only two actors could be run in parallel in this setup. Nowadays, multi-core systems allow for parallelism on a single computer, with some industrial chips having many dozens of cores. Since then, we've gone so much further. And Erlang takes full advantage of this possibility. So, what are they saying here? Erlang was only adapted to true symmetric multiprocessing in the mid 2000s. So they're saying like true symmetric multiprocessing happened later. All right, well, that's fair. Doesn't really affect us too much. Oh, this is from, I think, the video, the Erlang video. Back in the day, Erlang's development as a language was extremely quick with frequent feedback from engineers working on telephone switches in Erlang itself. These interactions proved processes based concurrency and asynchronous message passing to be a good way to model the problems they faced. Moreover, the telephony world already had a certain culture going towards concurrency before Erlang came to be. This was inherited from Plex, a language created earlier at Ericsson, and Axe, a switch developed with it. Erlang followed this tendency and attempted to improve on previous tools available. Erlang had a few requirements to satisfy before being considered good. The main ones was being able to scale up and support many thousands of users across many switches, and then to achieve high reliability to the point of never stopping the code. Scalability. I'll focus on the scaling first. Some properties were seen as necessary to achieve scalability. Because users would be represented as processes which only reacted upon certain events, i.e., receiving a call, hanging up, etc., an ideal system would support processes doing small computations, switching between them very quickly as events came through. To make it efficient, it made sense for processes to be started quickly, to be destroyed very quickly, and to be able to switch them really fast. So like basically they're saying processes would run, but they don't need to like actually do much unless an event happened, which didn't always happen all the time. Having them lightweight was mandatory to achieve this. It was also mandatory because you didn't want to have things like process pools, a fixed amount of processes you split the work between. Instead, it would be much easier to design programs that could use as many processes as they needed. Yeah, so pools are a way of, if things take a little bit longer to bring up or go down, you might create a pool, like a database connection pool, where making a connection to the database was kind of expensive, so you just reuse connections that you already made. Another important aspect of scalability is the ability to bypass your hardware's limitations. That sounds always good. Always good. There are two ways to do this: make the hardware better or add more hardware. The first option is useful up to a certain point, after which it becomes extremely expensive buying a supercomputer. The second option is usually cheaper and requires you to add more computers to do the job. This is where distribution can be useful to have as part of your language. So, yeah, having one computer with like a billion gigabytes of memory or more disk space or whatever might be more expensive than having several computers, just because of the way they scale and because of heat and electricity and all that kind of stuff. Anyway, to get back to small processes, because telephony applications needed a lot of reliability, it was decided that the cleanest way to do things was to forbid processes from sharing memory. Okay, so they were like, we're not going to share any memory. That made things clean. Shared memory could leave things in an inconsistent state after some crashes, especially on data shared across different nodes, and had some complications. Instead, processes should communicate by sending messages where all the data is copied. This would risk being slower but safer. Fault tolerance. This leads us to the second type of requirement for Erlang: reliability. The first writers of Erlang always kept in mind that failure is common. You could try to prevent bugs all you want, but most of the time some of them will still happen. In the in the eventuality bugs don't happen, nothing can stop hardware failures all the time. So like even if you write the best code, you might have like something break in your computer, a card go out, a circuit, whatever. The idea is thus to find good ways to handle errors and problems rather than trying to prevent them all. It turns out that taking the design approach of multiple processes with message passing was a good idea because error handling could be grafted onto it relatively easily. Take lightweight processes made for quick restarts and shutdowns as an example. Some studies prove that the main sources of downtime in large scale software systems are intermittent or transient bugs. Then there's a principle that says that errors which corrupt data should cause the faulty part of the system to die as fast as possible in order to avoid propagating errors and bad data to the rest of the system. Sounds like cancer, right? Like you have a cell, its genetic programming gets corrupted somehow, so it's making new cancer cells. So you really want to shut that down before it keeps working and screwing up the rest of the system. So similar concept here. Another concept here is that there exists many different ways for a system to terminate, two of which are clean shutdowns and crashes, terminating with an unexpected error. Here, the worst case is obviously the crash. A safe solution would be to make sure all crashes are the same as clean shutdowns. So, yeah, you can like do a clean shutdown, which sounds good, right? Or you can crash. So, what they're trying to say here is like, hey, wouldn't it be great if your crashes are basically clean shutdowns? This can be done through practices such as shared nothing and single assignment, which isolates a process's memory. Avoiding locks, a lock could happen to be unlocked during a crash, keeping other processes from accessing the data or leaving data in an inconsistent state. Yeah, so if you're holding a lock to some resource, like a file lock, and you crash, then that lock may still exist, and other processes or threads that try to access it will be stuck, right? That's not good. And the other stuff I won't cover more, but we're all part of Erlang's design. Your ideal solution in Erlang is thus to kill processes as fast as possible to avoid data corruption and transient bugs. Lightweight processes are a key element in this. Further, error handling mechanisms are also part of the language to allow processes to monitor other processes, which are described in the errors and processes section. Am I leaving? In order to know when processes die and to decide what to do about it. So there's ways for one process to basically link up, and I think the word is link or monitor. They're both terms used. Another process, and that means they'll get messages from the Erlang runtime system whenever a process dies or exits. Supposing restarting processes real fast is enough to deal with crashes, the next problem you get is hardware failures. How do you make sure your program keeps running when someone kicks the computer it's running on? Although a fancy defense mechanism comprising laser detection and strategically placed cacti could do the job for a while, it would not last forever. Look, this is like Hal from what's it called? Space Odyssey 2001. And then we have cacti. The hint is simply to have your program running on more than one computer at once, something that was needed for scaling anyway. This is another advantage of independent processes with no communication channel outside your message passing. You can have them working the same way whether they're local or on a different computer, making fault tolerance through distribution nearly transparent to the programmer. All right, this is a lot of speaking, huh? Anyone else there? Am I alone? Being distributed has direct consequences on how processes can communicate with each other. One of the biggest hurdles of distribution is that you can't assume that because a node, which is a remote computer, was there when you made a function call, it will still be there for the whole transmission of the call, or that it will even execute it correctly. Someone tripping over a cable or unplugging the machine would leave your application hanging, or maybe it would make it crash. Who knows? Well, it turns out the choice of asynchronous message passing was a good design pick there too. Under the processes with asynchronous messages model, messages are sent from one process to a second one and stored in a mailbox inside the receiving process until they are taken out to be read. It's important to mention that messages are sent without even checking if the receiving process exists or not, because it would not be useful to do so. As implied in the previous paragraph, it's impossible to know if a process will crash between the time a message is sent and received. And if it's received, it's impossible to know if it will be acted upon, or again, if the receiving process will die before that. So basically, they're saying it doesn't make any sense to check. Like you can check, like, hey, is this process still running? You would check, and then you would try to send a message, and just then it could crash, right? So unless you're constantly checking, which means you'll never actually get to send the message, right? So it just doesn't make sense to check. So it's going to send the message, and it goes in the mailbox, and we don't make any assumption that it will actually get that message or process it. Asynchronous messages allow, and that's why it's asynchronous, because we send it and then we fire and forget. Allow safe remote function calls because there is no assumption about what will happen. The programmer is the one to know. If you need to have a confirmation of delivery, you have to send a second message as a reply to the original process. This message will have the same safe semantics, and so will any program or library you build on this principle. So yeah, like, when we get to gen servers, we'll see that like there are synchronous message calls, like function calls over this mailbox system, but really it's asynchronous at its base. Um, and there is a delay. Basically, it's kind of hidden from you a little bit, but there's a max timeout time that's going to wait, and then it returns an error. All right, cool. We're up to a new section, implementation. All right, so it's decided that lightweight processes with asynchronous message passing were the approach to take for Erlang. Findus, I have no experience with Erlang, but as I see it, Erlang does not use the under concurrency model of the underlying OS. The concurrency model of Erlang is handled by the VM. Yeah, so Beam handles the handles the processes. However, like because it's actually using threads at some point, um, Beam does call into the operating system. Um, Beam, yeah, we're not kind of going down into the operating system level, but if it's running on Linux, it's going to be running, it's going to be calling into the Linux system for threads to be running. But processes are not like there's not a direct relationship between these processes and threads. So the Beam is going to be um, yeah, Beam is going to be um, basically creating the threads, mapping the processes, and like it has its own scheduling system. So it's like it knows when to call when a process should be running, and it also handles dirty processes. Um, and it is preemptive, like it can stop a process from running. So it can be like you're taking up too much CPU time, so we're going to switch. And it does that pretty evenly. Oh, here it is. Right. So there you go. But yeah, so processes. So if you have 1,000, or like literally, it's easy in Erlang and Elixir to create 1,000,000 processes. If you tried to create 1,000,000 threads on your OS, it wouldn't work well. But in Erlang, it's not a problem. But yeah, those will not spawn that many threads. All right, so it was decided that lightweight processes were good. Da 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 da. Where were we? Um, Operating systems can't be trusted to handle the processes. Operating systems have many different ways to handle processes, and their performance varies a lot. Most, if not all of them, are too slow or too heavy for what is needed by standard Erlang applications. By doing this in the VM, the Erlang implementers keep control of optimization and reliability. Nowadays, Erlang's processes take about 300 words of memory each and can be created in a matter of microseconds, not something doable on major operating systems these days. So, yeah, they're talking. To handle all of these potential processes your programs could create, the VM starts one thread per core, which acts as a scheduler. Each of these schedulers has a run queue or a list of Erlang processes on which to send a slice of time. Oh yeah, this is how like it's Erlang processes can actually be migrated from one queue to another, or basically one thread or core to another one. Um, and there's actually like priorities also that you can set on your processes. When one of the schedulers has too many tasks in its run queue, some are migrated to another. This is to say each Erlang VM takes care of doing all the load balancing and the programmer doesn't need to worry about it. There are some other optimizations that are done, such as limiting the rate at which messages can be sent on overloaded processes in order to regulate and distribute the load. There we go. So this would basically be a scheduler, and it would be associated with one core, and then each scheduler has a queue of processes to run. And if and there's some kind of like system of how it decides to migrate different processes from one queue to another. All the hard stuff is in there managed for you. That is what makes it easy to go parallel with Erlang. Going parallel means your program should go twice as fast if you add a second core, four times, etc. Is right? It depends. Such a phenomenon is named linear scaling in relation to speed gain versus the number of cores or processors. See the graph below. There we go, the graph. Number of processors. And then this one here, whatever problem this was, they added cores. It just doesn't help. It hits a limit. It looks like it's asymptotic. In real life, there's no such thing as a free lunch. Well, there are at funerals, but someone still has to pay somewhere. Not entirely unlike linear scaling. This is what I kind of have mostly specialized in. The kind of programming I do is like lots of threads. So, yeah, it depends on the problem you're trying to solve, like how much scaling you can get. I know funerals, it's so macabre. The difficulty of obtaining linear scaling is not due to the language itself, but rather to the nature of the problems to solve. Problems that scale very well are often, to be said, embarrassingly parallel. If you look for embarrassingly parallel problems on the internet, you're likely to find examples such as ray tracing, brute forcing searches in cryptography, weather prediction, etc. From time to time, people then pop up in IRC channels. This is an older book, forums, or mailing lists asking if Erlang could be used to solve that kind of problem or if it could be used to program on a GPU. The answer is almost always no. The reason is relatively simple. All of these problems are usually about numerical algorithms with lots of data crunching. Erlang is not very good at this. This is where you would use like Julia or C++ or, even Python with all of its native code libraries. Erlang's embarrassingly parallel problems are present at a higher level. Usually, this has to do with concepts such as chat servers, phone switches, web servers, message queues, web crawlers, or any other application where work done can be represented as independent logical entities. Actors, anyone? That's why it's the actor model. This kind of problem can be solved efficiently with close to linear scaling. The funny thing is, when the Erlang folks made Erlang, they didn't realize, I think, that the model they were going already existed. It was called the actor model, or was being created. So some dude like on a computer science side like called it the actor model and described it with mailboxes and everything, and the Erlang folks did it too. Um, and they're very very similar, but not exactly the same. But good enough that we call it the actor system model. Yeah, and like, anytime you think of like node where you're running something and you want to spawn another, like you have a promise that's doing something like this, often you would think, wouldn't it be nice if I could just run this in parallel, right? Um, and yeah, it can't. So these are higher level workers doing something. It could be like a database fetch, it could be like generating a web page or whatever because they're fairly independent. Sorry, I get allergies. Many problems will never show such scaling properties. In fact, you only need one centralized sequence of operations to lose it all. So as soon as you have like one thing that's centralized that everyone needs to do, all your parallelism kind of goes away. All your gains go away because they're all going to be crunched on this one thing, right? Your parallel program only goes as fast as its slowest sequential part. An example of that phenomenon is observable anytime you go to a mall. Hundreds of people can be shopping at once, rarely interfering with each other. Then, once it's time to pay, queues form as soon as there are fewer cashiers than there are customers ready to leave. So, that's the slowest sequential part. When you think of the sequence of going to a mall, it's like you go in the door, you look for your stuff, you pick your stuff, you try on the clothes, then you buy the clothes and leave, right? Trying on can be a slow sequential part depending on places. Like there may not be enough changing rooms to test to try on your clothes. That could be bad in some places, and other places it's checkout. I'm kind of glad that a lot of places have these like automatic checkouts now because but you know what's really annoying is when they have like 20 of them, but like 15 of them are just like off or broken. You're like, what the fuck? Like, what was the purpose? It would be possible to add cashiers until there's one for each customer, but then you would need a door for each customer because they couldn't get inside or outside the mall all at once. This is kind of an extreme example, right? But it's a little bit like imagine if it was like big numbers, right? And I guess like even highway systems are a little bit like this if you think sequentially like you have your on ramp, you're driving and then you move over to the left maybe depending if you're left side or right side driving. And then you have to exit and you have tolls sometimes. And like the merging is usually like a small lane, so that could be a limiting factor. The tolls, there's only so many um transactions those can do. So those would become a limiting factor. Yeah, it's interesting because you could either speed up that slow part or add more of them, right? A generalization of this principle is called Amdahl's law. It indicates how much of a speed up you can expect your system to have whenever you add parallelism to it, and in what proportion. According to Amdahl's law, code that is 50% parallel can never get faster than twice that it was before. And code that is 95% parallel can theoretically be expected to be about 20 times faster if you add enough processors. What's interesting to see on this graph is how getting rid of the last few sequential parts of a program allows a relatively huge theoretical speedup compared to removing as much sequential code in a program that is not very parallel to begin with. So when they say getting rid of the sequential parts, they're basically saying they're adding more processors because that's a little bit like adding cashiers. And so if it's highly parallelizable, then you'll get this huge 20 times thing. Um, and I guess if it's 100%, then it goes infinite, right? Because then the difference is zero. All right. Anyway, sorry, I got lost. Don't drink too much Kool-Aid. Parallelism is not always the answer to every problem. In some cases, going parallel will even slow down your application. This can happen when your program is 100% sequential but still uses multiple processes. So, if it's 100% sequential, then what's the point of having multiple processes? You just have the overhead of moving it between processes. One of the best examples of this is the ring benchmark. A ring benchmark is a test where many thousands of processes will pass a piece of data to one after the other in a circular manner. It sounds like token ring. Think of it as a game of telephone if you want. In this benchmark, only one process at a time does something useful, but the Erlang VM still spends time distributing the load across cores and giving every process its share of time. This plays against many common hardware optimizations and makes the VM spend time doing useless stuff. So yeah, this is you have like 5 nodes and they're basically whoever gets the item calls the next node and then they call the next node. So obviously while someone has the item, the other ones can't do anything because there's only one item. So you're just wasting time. It would have been a lot faster. It's representing basically having a while loop, right? Where you're just like spinning in this while loop doing nothing. And in a way that's super inefficient, but in a way it's super efficient because there's no overhead, it just spins. So long and thanks for all the fish. That was kind of for a while the last book in the Hitchhiker's Guide, so they took that. Of course, this chapter would not be complete if it wouldn't show the 3 primitives required for concurrency and Erlang: spawning new processes, sending messages, and receiving messages. In practice, there are more mechanisms required for making really reliable applications, but for now this will suffice. I've skipped around the issue a whole lot and I haven't yet to explain what a process really is. It's in fact nothing but a function. That's it. It runs a function and once it's done, it disappears. Technically, a process is also technically a process also has some hidden state such as a mailbox for messages, but functions are enough for now. To start a new process, Erlang provides the function spawn, which takes a single function and returns it. So here we go. Spawn, and it takes a function. Let's write it. Let's hide it and write it. All right, here's my coder. Uh, Erlang, here we are. We'll just call it concurrency is so long, but if I say con, it sounds weird because in French, con means asshole. Let's call it processes. Module processes. Compile. Is it export all? I think so. I'm starting to remember some of this stuff. Um, all right. We don't actually need this right now. We'll do Erl, and then we'll make a function. What's the format? Is it fun to make fuck? There we go. I have a function. And then I do spawn my function. There we go. We didn't see anything um because it ran it, but it's hidden. So let's make it actually print something out in console so we can see it. Is it format? I feel like I've forgotten everything. New line, end. Now let's try running it. Done, right? Now let's try spawning it. Okay, you see it says done. So we know it ran it. And let's try writing an anonymous function in here. I think we just do that, right? Look at that. We're like Erlang programmers now, guys. Look at that. Not a single syntax error. All right, let's see what it says. Yeah, here we go. Spawn, it didn't say anything. Oh yeah, so when we run it, we get this, and this is a reference. And I think a reference is also a PID, process identifier. So it tells us what process it is. That's what this is saying. You'll notice that we can't see the result of the function. We only get its PID. That's because processes do not return anything. How can we see it? Well, they did the same thing we did. They print it out. This isn't practical for a real program, but it is useful to see how Erlang dispatches processes. Fortunately, using IO format is enough to let us experiment. We'll start 10 processes real quick and pause each of them for a while with the help of the function timer sleep, which takes an integer value n and waits for n milliseconds before resuming code. So what is this doing? They have a function that sleeps and then prints something out. What's it printing out? X. The function that takes in X. And then we make a list and a list comprehension. And we get back a list of PIDs. All right, we can do this, guys. We can write this. We can do this. So we make a function g that takes in, what was it going to do? I've forgotten already. It sleeps for x something. I think it does sleep 10, and then it does IO format, and I think it prints out X right? Syntax error before G. There we go. So this X is, we give it the list and it puts it in here where the P is. So it's going to say X is equal to whatever the value of X is. And then we make a list comprehension. We're going to put the PIDs in here, right? So we're going to feed in a sequence. So this is going to make n 1 through 10. And then in here, we're going to spawn and we got to give it a function. Remember, our function can't take any parameters, so we'll make an anonymous function. And our anonymous function is going to call G, and it's going to pass in N. Does that look right? What do you guys think? So let's see. Let's see if we can just copy this. Copy it here. Okay, so we did this. So if I do G and I pass in a number like 100, it says 100. Sleep 10. That's 10 milliseconds. That's not enough. All right, so that worked. It waits a second and does that. And now it looks like it doesn't like this, but maybe that's just because it doesn't like this. Syntax error before. Oh, I need an end here. Undefined list sequence. Lists sequence, maybe. There we go. Look at that. So you saw it wait a second before returning all of these. I get back the PIDs immediately, but then they do their work a second later. We could make each one wait. Based on X. So if you pass, it'll be up to 10 seconds, right? Maybe we change this to 500 then. Oh, right, and I should fix this. Wait, it doesn't like this still? Oh, right. I didn't make it list. Let's fix that too. Hey, look at that. Isn't that cute? Let's see, what was it that they were doing? Sleep, spawn. Oh, is it Oh, it's random? Theirs comes out random because they do it all at once. But mine, I think, comes out in order. There it goes. We see some random numbers here, like changing because of the way it's scheduled. But we'll never see that if I make it sleep because it waits. Hi, Brainless Society. The order doesn't make sense. Welcome to parallelism. Because the processes are running at the same time, the ordering of events isn't guaranteed anymore. That's because the Erlang VM uses many tricks to decide when to run a process or another one, making sure each gets a good share of time. Many Erlang services are implemented as processes, including the shell you're typing in. Your processes must be balanced with those the system itself needs, and this might be the cause of weird ordering. Yeah, so like you don't know each time it runs something whether a core it got on the same queue or whatever. So if they all are going to run at the same time, then often it won't return in order. Where did I do the spawn one without the sleep? Oh well. The results are similar whether symmetric multiprocessing is enabled or not. To prove it, you can just test it out with Erlang VM Erl's SMP disabled. Alright, this doesn't matter. I don't care. To prove the shell itself is implemented as a regular process, I'll use the built-in function self0, which returns a PID of the current process. So we write in self, and it returns the PID of the shell. Exit self. So what happens? I see. So now when we run self, you see that we have a new number. The number is always the same until we exit. Then we have a different number because the system restarts the shell process. And the PID changes because the process has been restarted. The details of how this works will be seen later. This is the whole like let it crash concept. There's a supervisor that watches it and knows how to restart stuff. Um, let's figure out how to send messages around because nobody wants to be stuck with outputting the resulting values of the processes all the time and then entering them by hand in the other processes. At least I know I don't. The next primitive required to do message passing is the operator bang, also known as the bang symbol. On the left hand side, it takes a PID, and on the right hand side, it takes any Erlang term. The term is then sent to the process represented by the PID, which can access it. Okay, so I did not know this. This must be an Erlang thing and not an Elixir thing. So if I do self and I pass it, hello, here's an atom. It's not a variable. So what's going on? The message gets put in the process's mailbox. This guy self, our self. Like we can do self, you'll see that we are that, right? So we can call myself is equal to self. And then we do myself, which is a process now, bang, foobar. And then you can see that myself now gets foobar, and I guess it prints it. The second hello shown here is the return value of the send operation. So it just means that it sent it, doesn't mean that it was like processed. This means it is possible to send the same message to many different processes by doing, oh, you can chain them. Myself, self, foobar. It just like basically goes from right to left is probably the order of processing on this. A thing to note about a process's mailbox is that the messages are kept in the order they are received. That sounds like an answering machine. Coming from Elixir to Erlang, yes, exactly. I've been doing Elixir for a while, and I figured it's a good time. I went to a conference, Goatmeyer, and I noticed a lot of the good Elixir folks know Erlang, and they liked it. So I was like, oh, I just had this mentality of like Elixir's newer, so no point learning Erlang. But the more I look into it, the more I'm kind of interested in it, and it's kind of a neat language. So far, the thing I'm missing the most is the pipe operator. But otherwise, it's kind of fun. I like the syntax for their list comprehension. It feels very Haskell-like. The period and the semicolon and the comma, like that's a little annoying. Well, I have a whole set of I have a whole set of videos. So like you could go through this book on your own, and if you have any problems, then you can find the corresponding video on YouTube. I think my bio's on the link, and should that cause any problems. But yeah, I really love Elixir. All right, so I mostly use it on the server side. I like backend side. I don't do too much like almost no like Phoenix live view stuff, almost none. But I want to get into it. I'm going to be doing a talk in Berlin um for EU Beam Beam U Code Sync. I don't know. It's the Elixir Beam conference, and I want to use live view a bit for the presentation. All right, so we get it in the order it was received. Every message is read, taken out of the mailbox. Every time a message is read is taken out of the mailbox. Again, this is a bit similar to the introduction example with people writing letters. Yes. Live view is fun. I do mostly work writing APIs with Elixir, but I have a side project with live view. That's so cool. Yeah, like I don't like client front end programming, so live view sounds perfect, like let me just stick everything there. I know you could like still mix React and whatever, but I would just want to just stick with simple live view. To see the contents of the current mailbox, you can use the flush command while in the shell. So this is how we see the mailbox. Shell got hello, foobar, foobar, foobar. Now it's empty. This means we still can't bind the result of a process to a variable, but at least we know how to send it from a process to another one and check if it's been received. Sending messages that nobody will read is as useful as writing emo poetry. Not a whole lot. I don't get. Does this person like have something against emo poetry? I don't get it. This is why we need the receive statement. Rather than playing for too long in the shell, we'll write a short program about dolphins to learn about it. So dolphins will get a message, do a flip, fish, and something else. Let's write that ourselves. So we have the dolphin one function, and I don't even remember what it took as parameters. And it's going to call receive, I guess. I don't remember the format for receive. I'm guessing it's like, I'm guessing it's just receive. No, we probably need like a binding, like message. and then we can just, it's like case of, right? And then we'll do the message is, was it like flip? Got flip. I don't remember what the other one was, eat. And then something else which we don't know, and we'll say like, and all of these probably need to be semicolons because they're continuations. And I'm guessing this will need an end. Okay, didn't like it. Let's see, maybe it's a do. Let's see. Receive has nothing afterwards. They're passing atoms here. Oh, so this is valid code now. So let's pass atoms, flip, eat, and something else. So what this means is, I hate this thing here, so I'm just going to make this an export. Am I doing this wrong? Okay. So now, what, Control Shift Alt 2? Then, whoops. What is this doing? Oh, that's moving up and down. There we go. Now I can compile this, processes. And now I can do spawn and pass in dolphin1. Right? No? I forget the syntax for this. Is it like this? There we go. All right, so that spawned it. So now dolphin1 is running. Whoops, but I have no way to send it a message. Let's spawn it again, but this time we'll store it. Okay, so now dolphin1 has the PID, right? And now how do we send the message? All right. You do the dolphin1 and then we use bang and we give it a message like flip. And then you see it answered and said got flip, and then our thing returned flip. So we actually sent a message to another process and it ran. Probably on a different core. If we send it a flip again, it won't answer, I don't think. You see, it didn't say got flip because it's done. This process isn't looping. I remember there is a way to build the PID from string. Yeah, you can totally do it. But since we didn't learn it here yet, I'm not doing that. All right, so we can do it again. We just free up this variable. That erases the binding. And now I can spawn it again. And you can see that now I can say eat. And it says eating. Yay, running. Uh, oh look, they're doing something here. What is this? Spawn dolphins. Dolphin 1. So it's giving the module basically, followed by this, followed by probably the parameters that it takes. Rather than taking a single function, spawn3 takes the module function and its arguments as its own arguments. Once the function is running, the following events take place. The function hits the receive statement. Yeah, just we already know all of this. I think, this is nice, but we don't really need this. Now what they're getting at is like, hey, we're printing out stuff, but wouldn't it be better if like we could get a reply from this dolphin process rather than just looking at it print something out? Of course it would. Why am I even asking? I've mentioned earlier in this chapter that the only manner to know if a process had received a message is to send a reply. Our dolphin process will need to know who to reply to. This works like it does with the postal service. If we want someone to know answer our letter, error, right? If we want someone to know answer our letter, I think it's know how to answer. Know how someone to know how to answer our letter, we need to add our address. In Erlang terms, this is done by packaging a process's PID in a tuple. Yeah, so you just have to send your PID in the message that you send. Like we're sending like eat here, right? But you can imagine sending self comma eat, right? Um, and now when it got the message, it would know how to send you back an answer. And that's what they're doing here. So let's go ahead and write that. So here we're expecting our message to take in a PID. What should we call it? Should we call it PID or sender? I just like to call it PID. Okay, so we got PID now, and for each of these, we can now send back the message. Got flip. Eating. And done now. I typed it wrong. Don't know is I think what I wanted to say. Don't know what you're talking about. Right? But we need to put the PID in here. End. Okay, so that should do that. We can recompile now. And let's clear dolphin 1. So now we can spawn dolphin again. Spawn. Let's try to use the 3 argument version. We pass it the module. We pass it the name of the process, the function to call. And we pass it the arguments, the argument list, which is empty since it's no args. And then we have to capture this. All right, so this guy's running and he's looking for something that looks like this, right? So now we send Dolphin 1 a message. And it has to have our PID in the beginning. And which one of these should we call? Let's feed it. So let's say eat. Right? All right, so we passed it. Everything's happy. Theoretically, we should have a message now, right? Back from it. So what was that called? Flush. And you see here, shell got eating. So it got back eating from this guy. I think we've demonstrated it. We could have called receive also, right? Like, so we make dolphin 2. And we call dolphin 2 and we pass in just something else, right? And now we can call receive and we say and receive takes in the thing we got. So let's say we call it response and we're just going to return response. I think we got to call end. And now you can see it says don't know what you're talking about because we passed something else. Something else doesn't match any of these. So it goes into this one, this underscore, which is a wild card. And it says don't know what you're talking about. But flush is easier, right? Because it's less typing. Interesting, the error 1 doesn't return a message. It just prints. So what I see. So what they want to do now is to make this recursive. So what they're going to do is call back the function. The comma is to continue. Eating is really quit. My version is not very dolphiny. I'm sorry. That's why we don't call dolphin 1 here. Here we'll call ourselves back. We want to continue even though we got an error. All right. This is the last clause, so it doesn't need a semicolon. Last of the receive clauses. So this should work. This will basically loop, and we can keep sending messages. So we will clear that F just clears all the assigned variables, so I can use dolphin 1 again. Oh, it works. Compile it. And now I call that seems right. Except I'll call this dolphin1. So we spawned dolphin1, and now I should be able to do dolphin1, bang, and pass in self, comma, flip, and now if I call flush, you can see it got a flip, and I can keep calling these. And when I call flush, I should see three flips, right? Let's send a couple of flips, but then we'll send a weird message like tumble, and then we'll call flip twice more. So in order, we should see we got a response, flip, flip, tumble, flip, flip, don't know what you're talking about, error, don't know what you're talking about, and then flip, flip. Yeah. And then after I send a quit message, it won't process anymore. Right, so this should have exited the process, and now if I send it flips, and then I call flush, I won't see it. I won't see anything. Oh, I got the bye-bye from the quit, but then after that, I didn't get the flips. So that worked. What's going on now? Okay, so they added the recursion. We've done that. Do a flip, both loop. Yeah, tail end recursion. It's the last thing. So there's no stack issues that this could basically run forever. But if we sent the fish message, which we called quit, it exits. And that should be it for dolphins.url. As you see, it does respect our expected behavior of replying once for every message and keep going afterwards, except for the fish call. The dolphin got fed up with our crazy human antics and left us for good. Do a backflip. How about no? Nope. Why is the dolphin like Elvis or something? There you have it. This is the core. This is the core of all of Erlang's concurrency. We've seen processes and basic message passing. There are more concepts to see in order to make truly useful and reliable programs. We'll see some of them in the next chapter and more in the chapters after that. Wow, so they're going to do more multiprocessing. So we're going to stop now for Erlang. I don't know if I'm going to do more otherwise, but like, this, we're not going to do this chapter today. But that was fun, interesting, a lot of reading. Too much reading. Let's see what this next chapter is going to be for the next one, though. It looks like we're just building something on top of it. Right, so like we're trying to abstract. Notice like I had to keep like writing this code. It'd be nice if I had both a sender, like a client side function to make this call, and also perhaps like helper functions here too, so that they're just not in this like clause. But this is all on the same thing then, right? Where's the spawn? Ah, oh, so in Elixir, this is underscore underscore module underscore underscore, but here it's question mark module is the name of your module. This is just saying I only care about messages that match this. Don't take out other messages that don't match it. I don't usually write code like that. Anyway, that was cool. We're done. Let's see. We've done all of these type recursion, blah, blah, blah. Where we just did this. More multiprocessing, errors in processes. So this is probably how like you can send an error message over the network basically. We're going to do hot code reloading. We're going to start getting ready to learn OTP, which is really what makes Elixir Beam awesome. Clients and servers. I'm curious what this will be about. This is probably just more coding. Supervisors. OTP app. How to patterns to build OTP apps. How to do releases. Yeah, this is really cool. ETS is sort of like a Redis built into Beam. Distribunomicon. And then this is probably when we run it on multiple computers. How we probably recover state when on a crash. Type specs, these are kind of important. This is like, because you notice a lot of the functions we write don't have any kind of like type testing. So Dialyzer uses type specifications that are it does static type analysis. So you can do it like basically at compile time to tell you if you have typing errors. Yeah, so if you guys like this book, go ahead and order it too. Help the author make money. All right, I'm going to break now. I don't know if I'm going to continue streaming. I'm kind of thinking to. I'm not really sure. I'm kind of thinking either I ordered a Commodore 64 because Commodore relaunched. And I was learning Atari assembly, but like now I'm kind of like thinking like, well, since Commodore is not a dead computer anymore, maybe I should like learn assembly on that instead. I feel bad switching, but like I don't know, maybe it'll just be more relevant, because the machine will exist. But it's also 11 p.m. and I'm kind of tired. How to decide. See you. Take care. Thanks for joining. I think I'm going to stop now. Yeah, just like better just to stop now. And we'll do more Erlang hopefully tomorrow. So see you guys later.